This is part 2 in a series of videos I'm making on trying to deal with noise on the Altair 8800 and trying to make it a bit easier to fit cards without the problem that's associated with the noise that the machine generates on the various buses and on the front panel. Before I went into any more depth in the Altair itself, I just wanted to do a quick video showing the complexities of trying to look at something like this, and in particular why some of the causes of strange behaviour are so hard to track down. What I've got set up here is a representation of a TTL logic gate, or a very simplified TTL logic gate, but it does operate with very similar parameters to a 7.4 series chip. And what we're looking at on the scope is the output of the gate. It's running at 5 volts. As I say, all the resistances are very closely matched to a 7.4 series device. The only real difference is we've kind of got what amounts to a PCB behind the gate in terms of the breadboard. And what I'll try to do here is match this to what I see on the actual boards within the Altair itself. It's running at 200 kilohertz, it's got a square wave input, and the first thing we'll look at is the schematic for this, so it's clear what we're actually trying to simulate. So we've got a 2-input gate. It's a standard emitter input gate. As I say, the impedances are set to give us something as close as possible to a TTL gate, and we're monitoring the output here. How it's running at the moment is we have power 5 volts coming straight into the breadboard. We have the input resistance set to 150 ohm. That seems to be fairly typical as to what we see on the cards that are in the Altair. And at the moment it's drawing 28 milliamps at 5 volts. Now the first thing to note is that the edges I'm feeding this are quite steep, they're quite fast. But what you tend to find as the noise takes over within the system is you can get a situation where the rising edges are quite slow. And although I haven't really found that to be much of a problem with the Altair, just to be complete, what I'll do very briefly is switch the signal source into a slower switching source, and you can see that that actually kills the output of the gate. Although it's still switching to the same amplitude, the gate is not turning on or off, and the current consumption has nearly doubled. That is what you tend to find with TTL chips if you start feeding them slow rising or slow falling inputs, because of the nature of the output. Both output transistors spend too much time turned on, and that can cause the gate to become unstable. And that's even worse across a package, where if you got 4 or more of these gates and the inputs are not within specification in terms of switching speed, that can make the entire chip behave in a strange manner. So even though it may only be one input to the chip that's causing the problem, the entire chip can look like it's faulty or misbehaving, and the fault can actually be somewhere entirely different. Having said that, that's not something I've found much of within the Altairs that I've been looking at. What I'm going to do now is change some of the parameters within the setup we've got here in terms of capacitance or inductance to simulate the differences in putting boards or rerouting wires within the Altair, and show you just how much of an issue this can cause. So it looks like we're nice and stable here. I've got channel 2 of the scope hooked up to the incoming power supply. So if I turn channel 2 on, I'm sure straight away you can see a very familiar looking pattern. If you've ever examined the Altair data buses or address buses, you'll see this quite a lot, and it's fairly severe ringing on the in this case it's the power coming into the chip. This is not the power supply. I've tested this with batteries and it does exactly the same thing. So this is a genuine artifact of this particular circuit. where it gets a bit strange, and this is something that's been very much borne out in the testing I've done with the Altair. Well, at the moment there's no real capacitance other than stray capacitance on the power rail coming into this breadboard, and it's a fairly low impedance path. It's less than 0.1 ohm, which again is typical of the Altair source impedance or source resistance for the power supply. What I'm going to do is put a 100 nanofarad capacitor across the power rail, and you'd think that that would clean up this this noise on the power rail. So I'll plug this in now, and it's kind of slowed the input down, but it's actually made the spikes bigger, so the peak deviations are now much higher than they were. And if we zoom in terms of speed, you can see that what's happening is we've changed the nature of the ringing. So I'll zoom back out. I'll take the capacitor back out. Now, one of the things with the Altair, especially the bigger motherboards, so 12 or 16 or 18 slot motherboards, is they have a lot of inductance on the traces going across the board. So I'm now going to introduce a very small inductor. This is only a few microhenries, and this is in the power rail. So as you can see on the scope, it's gone completely haywire. We've got ringing now that's much larger than the signal. Incidentally, these voltages are identical to what you would see with a standard TTL gate. As I say, this is almost identical to the performance of a TTL gate. But you can see this small amount of inductance has really upset the circuit. Power drawn, the current drawn is still identical, it hasn't changed, it's 28 milliamps, but you can see that the entire thing has become very unstable. And I've done quite a lot of work studying this, so it's not the way I've got the probes hooked up or anything like that. This is something I see in the actual Altairs as well. So what I'm going to do now is put the capacitor back on the power rail. So you can see a fairly familiar pattern. If you've ever done this sort of thing, you can now see that the switching currents are causing the capacitor to charge and discharge over each cycle, which is what you'd expect. If I now put another capacitor in, you can see that the situation is getting much better. This thing that might be a bit strange is this. This spike here is caused by the switching of the output transistors in the gate. And again, the reason I wanted to do this is so that as I go through the Altair in the following videos, is we'll see things very similar to this, and this approach in terms of trying to sort out the inductance and the capacitance within the system is what I was aiming at and what I was trying to find in order to deal with the issues I was having with the Altairs. There are ways around this once we've traced what the problems are, but one of the difficulties with the Altair is there's a huge amount of interaction between the various cards and boards, largely down to the physical layout of the machine. As I said in the previous video, the wires going to the front panel are really a huge problem. But in the Altair I showed in the last video, I've dealt with most of this and I'm now getting very good clean signals on the buses, and I want to go through the various steps I took to get that. I didn't really do much in terms of physically modifying the Altair, and that was the real goal. I didn't want to start modifying the machine. I wanted to keep it as genuine as possible, but I wanted to be able to use it, and how it was, I couldn't use it at all. One or two cards worked. Sometimes they'd work fine, sometimes they'd misbehave. Loading basic sometimes took 3 or 4 attempts, and it ultimately came down to these issues with noise and interaction between various cards. That's it for this video. If you've got any questions about this, then please let me know. But as I said, the point of this was really to introduce the sorts of things we'll be seeing when we start investigating the Altair itself.